Hi, today we will talk about the biostatic mechanics. Biostatics is the science of interaction between a human body and forces acting on it. So, biostatic mechanics represents the fundamentals necessary for human factors engineering. We need the body to be in equilibrium. So, when being attacked by a force or carrying a load, our bodies should not move. Therefore, we need to consider the size of humans as well as the forces acting upon it. Static equilibrium equations. Newton's first law states that in order for a rigid body to be in static equilibrium, that body must be not only in translational equilibrium, but in rotational equilibrium. For translational equilibrium, what do you mean by that? Any force acting on the body, if horizontal or vertical, the body should resist it. So the body is going to create an inner force which is equivalent to the external force. Therefore, the sigma force in x direction or in y direction must be equal to 0. Now for rotational equilibrium, the net external moment at any point in the body must be equal to 0. Otherwise, the body will rotate. Therefore, sigma moment at any point should be equal to 0. Let's see an example here to understand the concept of statics. Here we have a horizontal lamp pole, which is a uniform horizontal beam of weight 100 Newton. It is hinged to the wall at point A. The other end of the lamp is supported by a cable here at point B, making an angle theta of 50 degrees with the horizontal. Now, the length of the pole is 1.33 meter. The lamp itself has a weight of 25 Newton, and the center of mass is located here at the middle. We will refer to this as point C. You need to understand that since it's hinged at point A to the wall, this means that rotation can occur here. At the other end of the lamp here at point B, it is supported by a cable. So here, tension could happen because the cable is pulling the lamp upward at an angle of 50 degrees. The length of the lamp pole is 1.33 meters, so this is distance AB. So distance AB equals to 1.33 meter. We have the weight of the lamp itself of 25 Newton. We need to solve for the forces in the cable, F, and for the horizontal and vertical reaction forces at the hinge joint. So due to the forces that we have and the weight of the lamp at point B, the hinge should resist these forces or else it will fall down. So we will have a resistance force in the x direction and in the y direction. Before starting with any calculations, the first step is to draw the free body diagram. It looks like this, and it represents the whole problem in a straight line. We can see that we have the straight line AB. C, as we said, is the center of mass of the pole, weight of the pole, and we have here the weight of the lamp itself. We can also see the force in the cable at a degree of angle of 50 degrees, which is theta. At point A, this is the hinge. We can see the reaction in the x direction, Rx, and the reaction in the y direction, Ry. So this should be the starting point in any solution drawing the free body diagram. Let's refine the free body diagram to indicate all the parameters that we have. We know that WP is 100 Newton, WL of the lamp is 25 Newton. But the F force here, we need to translate it into X and Y direction. So this force F will be translated into Fx and Fy. Fx would be F cosine theta, which is 50 degrees, while Fy will be F sine theta. We also know that distance AB is 1.33 meter and distance AC is half of it, so it is 1.33 over 2, which is 0.665 meters. Now let's begin with the solution. We need to find the values of Rx, Ry, and F. And in order to do that, we need to get sigma moment at point A and set it equals to 0. So let's look at the forces that we have. The first one is the weight of the pole, which is 100 Newton multiplied by the distance from point A. So this is the 100 Newton. The distance is AC. We will consider that since this force is going downward clockwise, so we'll give it a negative sign. And the anti-clockwise, we will consider it as positive. You can set it oppositely if you want. It doesn't matter because you will get the same answer but in different sign. So putting it here at the equation, remember that at point A at the hinge, we don't want to have any rotation. So sigma moment at A equals to 0. So we said that the weight of the pole is clockwise, so we set it as a negative sign, okay, and multiplied it by the distance to A, which is AC. Now we have the weight of the lamp, the 25 newtons. It's far away from A by distance AB. So again, it's this in a clockwise direction. So minus weight of the lamp multiplied by the distance AB. And we have the force F. We have that it's translated into Fx and Fy. So here we have Fy in the anti-clockwise direction. So plus Fy, and it is away from A by distance AB. So these are the forces that we have. We set sigma MA equals to 0. So we just add in the values that we know. The weight of the pole is 100, distance AC is 0.665, weight of the lamp is 25, and distance AB is 1.33. Fy, as we agreed, it is going to be equal to F sine theta. So F sine 50 degrees is equal to 0.766, and it's multiplied by distance AB, 1.33. We set this equals to 0 in order to get the force F, which is 97.8 Newton. Now the second step in the solution is to get sigma of x and sigma of y. When we take sigma of x equals to 0, we get Rx equals to Fx. So this is the force and this is the reaction to it. So Rx equals to Fx, and these are of different opposite directions. So we can say that Rx minus Fx equals to 0. Setting it into the equation, we already know that Fx equals to F cosine theta, which is 50 degrees. So we can get Rx, it will be 62.9 Newton. Similarly, we will get sigma forces at y direction and set it equals to 0. What do we have at point A? We have Ry upwards, so we'll give it a positive sign. At point C, we have the weight of the pole downward, so negative sign. At point B, we have the weight of the lamp, 25, we'll give it a negative sign. And we have Fy, positive sign, and we know that it's equal to F sine theta. So we set all these forces in our equation, and we set it equals to 0. So we have Ry minus Wp minus Wl plus Fy equals to 0. In order to get the value of Ry, in this case it will be 50.1 Newton. So this was the solution of the problem. We get the value of the force F, and we got the value of Rx and Ry. You can see that the problem that we solved together is a simple fundamental engineering static system. So for the purpose of a human factors engineering, the system is the musculoskeletal system, muscles and the skeletal system. So the human factors engineering applies the biostatic analytical models in two different ways. The first one is the external forces acting on the human body, for example, the load that we carry. And the second one is the internal forces generated by the contracting muscles, which is how the body will react while we are carrying the load. Now, the first system that we will work on is the shoulder and the arm. The anatomical system for the shoulder and the arm consists of 4 parts. The first is the bone of the shoulder, the bone of the arm. These 2 bones are held together by the joint and the muscle that we will refer to as the deltoid muscle. So we have 2 bones connected together with a joint via a muscle. The main role of the muscle is to hold the bones together. If the muscles are not there, the bones or the skeleton will fall apart. Also, the muscle has a job, which is to carry the resisting force of an external force or an external load. However, this generation of the internal force or resistance force makes the muscle get tired. And this is what we call as fatigue. When the muscle gets tired, it will not be able to generate this resistance force. So it's our job in ergonomics or human factors engineering to modify the tasks in order to reduce the force exerted by the muscles. So by doing that, the muscle can carry loads for more period of time before getting fatigue.